In this video, we will discuss about one-to-one functions and inverse functions. Horizontal line test is used to identify whether the graph of a function is a one-to-one. For example, identify which of the following is a one-to-one function. For letter A, the given is a mapping diagram, and we can see that this is a one-to-one mapping. For letter B, the given is the graph, and using horizontal line test, we can see that horizontal line intersect the graph in 2 points. So letter B is not one-to-one. For letter C, using these ordered pairs, 7, 1 and 5, 1, we can see that the mapping here is many to 1. So this is not a one-to-one. Letter D is also given as a graph, and if we draw a horizontal line intersecting the graph, it will intersect at most 1 point in any part of the graph. So this is a one-to-one. And letter E, the graph is horizontal line. So if we will draw horizontal line intersecting this horizontal line, it will intersect in infinitely many points. So this is not a one-to-one. And for letter F, drawing horizontal line, so it intersects the graph in at most 1 point. So letter F is a one-to-one. So the only one-to-one function here is letter A, letter D, and letter F. If f is a one-to-one function, then the function f has an inverse denoted by this. This diagram shows the inverse function. Suppose, for example, we have an input x, and applying the function f, the output is f of x. And then this output of f will now be the input of another function, which is f inverse. So from the input f of x, if we will get the inverse of f, so the output is x. So as we can see here, the domain of the function is the range of f inverse, and the range of the function is equal to the domain of the f inverse. So let us apply inverse function in this example. Let f be a one-to-one function. For the first question, if f of 5 is equal to 2, then what is f inverse of 2? So to identify or illustrate f of 5 equal to 2, let's have this set notation. So 5 is in the first set and 2 is in the second set, and the mapping is the function f. So this shows the mapping of f of 5 is equal to 2. And then doing the f inverse, which is the inverse notation of f or inverse operation of f. So f inverse is this. So the input is 2 and the output is 5. So that's why f inverse of 2 is equal to 5. For the second question, if the domain of the function is 5 to infinity, then the range of its inverse is. So since we know that the range of f inverse is equal to the domain of the function, so it means to say the range of f inverse is still the same as 5 to infinity. For the third part, so given the graph of the function given on the right side, we will evaluate the following. F of 1. When we evaluate f of 1, we're looking for the y value when x is equal to 1. And the y value when x is equal to 1 is at this point, the y value is 0. And then for the second, finding the value of f inverse of 1/2 means we are finding for the x value when y is 1/2. So when y is 1/2, x is equal to 2. And then for the third part, we will draw the graph of the inverse function. Since this is the graph of f inverse, to graph the inverse function, we know that the graph of the function and its inverse is symmetric with respect to y equal to x. So it means what we're going to do is we will interchange the x and y coordinates of every point. For example, in this negative 2, if we will interchange the x and y, it will be the same point, which is -2, -2. And then for 0, 1, 0, negative 1, we will interchange this, so it will be negative 1, 0. And then 1, 0 will be 0, 1. And then 2, 1 half will be 1 half, 2. And then connecting these points according to this or based on this, so we will have this graph of f inverse. And you can see that this graph of f inverse is symmetric with y equal to x. Let us have an important theorem regarding inverse of a function. If f of g is equal to x and g of f is also equal to x, then f and g are inverses of each other. Let's apply this theorem in this example. Let f be given as 2x minus 3 and g be given as a rational function which is x plus 3 over 2. The question is, are the functions f and g inverses of each other? So to answer this, we can apply or we can verify from this theorem because it says here that f and g are inverses of each other if the composition of function f of g is equal to x and composition of function g of f is also equal to x. So first, let us find f of g. In finding for f of g, we will put the function g for every x in the given function f. So it will give us 2 times, instead of x, we will write the function g, which is x plus 3 over 2, and then minus 3. And then evaluating this, so 2 times this fraction, it will cancel out the 2. So it will give us x plus 3 and then minus 3. And x plus 3 minus 3, 3 minus 3 is 0. So the answer is x. So it means f of g of x is equal to x. Then the other composition is g of f. So let us check what's the value of g of f. G of f means we will put the function f inside g in its value of x. So copying this g, x plus 3 over 2, but placing this x as a function f, so we will get this. And then simplifying the numerator, 2x minus 3 plus 3, it's equal to 2x, and then divided by 2. And then cancelling out the 2, it will give us equal to x. So g of f is also equal to x. So we can say here that since f of g is x and g of f is also equal to x, then we can say that f and g are inverses of each other. So there's another question. If the question is, if f of g is equal to g of f, then f and g are inverses of each other. The answer on this statement, it's false. Because to be inverses of each other, as we said in this theorem, f of g must be equal to x and g of f is equal to x. It doesn't mean that if they are equal, there's always equal to x. So the answer here is false. In example 3, if the graph of f inverse lies in quadrant 1, then in which quadrant does the graph of f lie? So a theorem states that the graph of a one-to-one function f and its inverse are symmetric with respect to the line y equal to x. So graphing a line y equal to x in the graph, so it will look like this. And then to answer the question, let us assume a graph of f inverse that lies in quadrant 1, suppose for example a point, and then reflecting this across this line, so the graph of f will still lie in quadrant 1. And then let us extend this question if the graph of f inverse is in quadrant 2, 3, and 4. So let's start with quadrant 3. So if I assume a point of f inverse in quadrant 3, like here, and then reflecting on y equal to x, so it will lie on the same quadrant, which is also quadrant 3. And then suppose, for example, that the graph of the function is in quadrant 2, and then reflecting on this line, so the graph of f will be in quadrant 4. And the other way, if the graph is in quadrant 4, So the graph of its inverse is in quadrant 2. Now, in finding the inverse of a function, we will follow four-step rule. So in this example 4, we will find inverse of the following functions and then determine the range of f and f inverse. So the given function is a linear function, f of x equal to 1 half of x minus 4 plus 3. So for step 1, replace f of x by y. So we are replacing this f of x by y. Step 2, interchanging the x and y. Replace x by y and replace y by x. So in this equation, so it will be like this. We replace y by x and x by y. And then for step 3, solve for y. So since y is in this term, so we have to isolate this term. So moving 3 on the other side. So it will give us x minus 3 equal to 1 half of y minus 4. And then getting rid of this 1 half because we're solving for y here. So we can multiply both sides by 2. So 2 times x minus 3 is equal to y minus 4. And then isolating the y, moving negative 4 on the other side, and distributing this 2 in x minus 3 at the same time. So we will have 2x minus 6. Then moving negative 4 on the other side, it will be plus 4. And simplifying this, so y, it will give us 2x minus 2. And then for the last step, replacing y by f inverse notation. So y is replaced by f inverse of x, which is equal to 2x minus 2. So this is the answer for the first question, finding the inverse of the given linear function. Next is, we will also find the range of f and the range of f inverse. Finding the range of a function or any function is easier if there's a graph. Since there is no graph, so we can relate the range of f as the domain of its inverse. So range of f is equal to the domain of f inverse. Since we have a given f inverse, then we can find the domain here, which is all real numbers because 2x minus 2 is a polynomial or a linear function. So it's equal to all real numbers or negative infinity to positive infinity. That is the range of the function f. And then for the range of f inverse, we can relate it to the domain of f. And the domain of f will depend on this, since this is a linear function or a polynomial function, and its domain is all real numbers as well. Now for the second part of this question, the given function in B is a rational function. So using step 1, replacing f of x by y, so we replace this function f of x by y. And then for step 2, interchanging x and y, so this y will be x and x will be y. And then step 3, we're solving for y by cross multiplication. So if we cross multiply this equation, so it will give us x times y minus 1 and then equal to 2y plus 1. So since we are solving for y here and y is present on the right side and on the left side, so let us open the brackets here. So it will give us xy minus x equal to 2y plus y, and then isolating the terms with y on the left side, so we will move 2y on the left and moving negative x on the right side. So xy minus 2y is equal to x plus 1. And then isolating the y, let's factor this out. So factoring out the y, so the other factor is x minus 2, which is equal to x plus 1. And then now we can be able to solve for y by dividing both sides with x minus 2. So it will give us y equal to x plus 1 over x minus 2. And then for the last step, replacing y by f inverse notation. So f inverse of f is equal to x plus 1 over x minus 2. So this is the answer for the first question. And then now we will find the range of f, and as we said, it's easier to relate this as the domain of its inverse. So range of f is equal to the domain of f inverse, and looking back at f inverse, we can find the domain here since this is a rational function, and any rational function, the denominator cannot be 0. So here, the domain would give us all real numbers except 2 because the value of x that makes this 0 is 2. So that is also the range of the function f, all real numbers except 2. And then to find the range of f inverse, we will equate it to the domain of the function f. And since the function f is a rational function, here we know that x minus 1 cannot be 0 or x cannot be 1. So the domain of f, which is equal to the range of f inverse, is all real numbers except 1. Now for other examples, given f of x equal to this polynomial with variable x and a, and g of x equal to 2, find the value of the variable a such that f of g is equal to g of f. So here, we can be able to find a, the variable a, only if we equate these two composition. So to equate these two, let us find first f of g. So in finding for f of g, we will put the g function inside the f. So we will have, putting these two here, so 2 times 2 cubed minus 3 times 2 squared plus a times 2 plus 2. So this is placing g of x for every x in the given function. Then, evaluating this, it will give us 6 plus 2a. So this is our f of g. Next, let's find for g of f. To find for g of f, we will put the function f in every x of the given function g. So since here g of x is a constant function, for any value of x, the output or the y value is always 2. So the answer here, if you will replace that in x, the answer is also 2. So now we can equate the 2. F of g of x is equal to 6 plus 2a, and g of f is equal to 2. So we are now equating 6 plus 2a equal to 2. And then we can now find the variable a in this linear equation by moving 6 on the other side. So it will give us 2 minus 6. And 2 minus 6 is negative 4 equal to 2a. And then dividing both sides by 2. So it will give us a value as minus 2. For the second example, if f of g is equal to this polynomial and f of x is equal to x squared plus 1, then find g of x. So to find for f of g, since we have a given f of g here, we can start from this function by solving f of g again, by putting g of x inside the function f for every x. So it will give us g of x placing in x, it will give us the square root of g plus 1 instead of the square root of x plus 1. And then since this is the f of g, and we have given f of g here, so we can equate the two. So this square root of g plus 1 will be equal to this polynomial. And then solving for the square root of g, we will move 1 on the other side, and then simplifying the right side will give us this polynomial. And since this polynomial is a perfect square trinomial, we can factor this as a square root of 2x minus 3 in relation to square root of g of x. We can get square root of both sides to get rid of the power 2. And then getting square root of both sides, we can come up with g of x equal to plus and minus 2x minus 3. So there are two possible function g. The first is 2x minus 3. The other one is negative 2x plus 3.